Assalamu alaikum wa rahmatullahi wa barakatuh. Hello everyone. Welcome to lecture 13, Organic Chemistry 3. Carbohydrates and Nucleic Acids. To continue on with reactions of monosaccharides, today we will talk about the reactions with phenylhydrazine and Osazone formation. When treated aldose with phenylhydrazine, as expected, we get the corresponding hydrazone as any carbonyl compound. So when we react the mannose with aldehydic functionality with one equivalent phenylhydrazine in ethanol, we get the dimannose phenylhydrazone with double bond in here. Surprisingly, the reaction does not stop at this stage, but the reactant consumed two more equivalent of phenylhydrazine and gets phenylosazone as a final product. See, we have here double bond, N hydrazone, and carbon number 2 also became hydrazone. So this piece hydrazone called osazone. Several mechanisms were proposed by scientists. The best one is that the aldose react with phenylhydrazine to form hydrazone. Then the NN bond rupture proceeds intramolecularly in 6-member ring to form the imine and carbonyl at carbon 1 and 2. Then attacks by two equivalent phenylhydrazine to form the osazone. Well, they started phenylhydrazine N15 isotope labeling. So the hydrazone will contain N15 until we get to the intermediate. Still N15 is there, right? Now they found that the final product does not contain the N15 and only N15 is on ammonia, which means that we have this as an intermediate, then attacked by, replaced by the phenylhydrazine on carbon 1 as well as on carbon to another molecule we attack on here. So there will be no N15 on the osazone, only on the ammonia. To read more about it, go to tetrahedral, volume 21, page 2771, 1965. Read more. Ether and ester formation. Because of their multiple hydroxy groups, sugars can be converted into alcohol derivatives. Thus, most monosaccharides react with alcohol under acidic conditions to yield cyclic acetal. We call it glycosides. Glycosides are named as derivatives of their parent carbohydrates. Term pyranose indicates that we have 6-membered ring. Term pyranose is used for the 5-membered ring. So here is the sugar in the hemiacetal form react with methanol HCl gas to form methyl. Here is methyl. Then the name of the sugar alpha D-glucopyrano, and then end up with side, pyranoside. In this case, OCH3 is up, it's beta form, so it's methyl beta D-glucopyranoside. Since they are diastereomers, they can be separated by fractional crystallization. Recall that we have carbonyl react with alcohol to form hemiacetal. More we get the acetal form OR. The mechanism for the O-methyl formation at the anomeric carbon, it's protonated, then elimination of water by participating the lone pair of the neighbor oxygen to form the cation stable via resonance. Then the methanol will attack from the upper or the bottom faces or front and back sides to form alpha and beta products. Like other acetals, glycosides are stable to beta. But in dilute aqueous acid, they hydrolyze back to their parent. So if I have methyl glycoside, dilute acid and heat, we get back the hemiacetal, get back the carbohydrate to the hemiacetal structure. To complete methylation of Pyranose, we use methyl iodide with silver oxide catalyst or methyl sulfate. Methyl iodide with silver oxide as a catalyst will form as a complex and activate the CH3 group as a strong electrophile. So the OH will attack on the carbon to form this protonated species, which deprotonate to form the ether, the O-methyl bond. The glycoside is an acetal. As we mentioned, it is stable in base. So treatment of a glycoside with sodium hydroxide, methyl iodide, or dimethyl sulfate gives the methylated carbohydrate. If we start with glycoside, then we have 1, 2, 3, 4 OHs, which can be easily methylated with dimethyl sulfate in basic media to form methyl. This is the one, and then 2, 3, 4, 6 tetra O-methyl alpha glucopyranoside. That's how we name it. With dilute HCl and heat, we get this methyl easily, selectively, and we keep the rest of the methyl group, which needs much more hard condition. The presence of neighboring pairs of hydroxyl group in sugar allows for the formation of cyclic ether derivative. Such process work best when the OH groups are positioned cis to allow a relatively unstrained 5 and 6 member rings. Here we have two neighboring OH. We react them with carbonyl or acetal in presence of acid as a catalyst. We get, if we start with acetone, we get acetone acetal, or we call it acetonide. Okay? If you would like to read more, go ahead and read chemical review of the year 2001, volume 101, page 53. Ethers are used as selective protecting groups in carbohydrate chemistry. Glucose exists in three structures: open, 5-member ring, and 6-member ring. When we react glucose with acetone and acid as a catalyst, we find out that it reacts with the 5-furanose structure, OHs, and on carbon 1 and 2 OH, and on carbon 5 and 6, giving the diacetamide analog. The methyl alpha diglucopyranoside, it's already protected on carbon 1. We find carbon OH on carbon 2 and 3 are in different phases, while the OH on carbon 3 and carbon 4 and 6 OHs are close to one another. So when we react these species with the acetal of benzaldehyde and H plus as a catalyst, we get the benzylidene on carbon 4 OH and carbon 6 OH, leaving the OHs on carbon 2 and 3 free. So we get 4,6-O-benzylidene alpha glucopyranoside. To read more on that, go and read Journal of Chemical Education, volume 83, page 782, year 2006. The trityl group, triphenylmethyl, is so bulky that it tends only to fit on primary alcohol. So when we react the alpha glucopyranose containing only here one primary alcohol, if we react that with trityl chloride, we will get the O-trityl on carbon 6 only. The deprotection can take place using trichloroacetic acid. We can also easily convert only primary alcohol or primary hydroxyl group to silyl ether. So using bulky trisubstituted silyl halide like tri-isopropyl silyl or tertiary butyl dimethyl silyl or tertiary butyl diphenyl silyl, we can protect only again the primary hydroxy group. Reacting the diglucopyranose with tertiary butyl diphenyl silyl chloride in presence of dimethyl aminopyridine as a catalyst in pyridine solvent at room temperature, we get the O-silyl at carbon 6. So we get 6O-TBD-BS diglucopyranose as a product. To deprotect, we use tributyl ammonium fluoride. So fluoride ion as a deprotecting agent here. Sugars are most commonly converted to their silyl ethers to make them easier to handle and sufficiently volatile for gas chromatography and mass spectrometry. So we have here diglucopyranose with excess trimethyl silyl chloride and triethylamine as a catalyst, we get 1, 2, 3, 4, 5 beta O-silyl analog. If we use glucose for gas chromatography, it will not survive the high heat, so it will decompose and it will not vaporize instead of it charring in the column of the chromatogram. So to make it much more easier for us to analyze carbohydrates, we transfer it to the silyl, like trimethylsilyl derivative of glucose. It's more volatile. It will survive at low temperature and go to the gas chromatography and mass spectrometry. Esterification. The hydroxyl group of carbohydrates, like those of other alcohol, can be esterified. So glucose pyranose with excess acetic anhydride in pyridine will give 1,2,3,4,6 beta-O-acetyl D-glucopyranose. Ester derivatives of carbohydrate can be saponified in base or removed by transesterification with an alkoxide such as methoxide. So we have here the beta-O-acetyl in sodium methoxide methanol. We get the D-glucopyranose and the methyl acetate. Outline a sequence of reaction by which D-glucose can be converted into methyl 2,3,4,6 tetra-O-acetyl D-glucopyranoside. We would like to get to that structure. Methyl at carbon 1, glycoside, and 2,3,4,6 tetra-O-acetyl. Well, the first step, we start with D-glucopyranose reacted with methanol HCl to form the methyl glycoside. We have now OH at carbon 2, 3, 4, and 6 free. We add excess acetic anhydride in pyridine and we get the desired molecule, methyl 2,3,4,6 tetra-O-acetyl D-glucopyranoside structure. Starting from dimanose, propose a synthetic scheme to form R,2,2-dimethyl 1,3-dioxylane for carbaldehyde. Well, this is structure of the target molecule, starting from dimanose structure. Well, if you would like to do that, first we reduce carbon 1 with sodium borohydride to get alcohol here. Now, this O and this O are close to each other. This O and this O are close to each other. When we react that with acetone or the acetal of acetone using 10-chloride Lewis acid, we get the acetonide on carbon 1, 2, 5, and 6 diacetonide. Now we have only 2 free OHs adjacent to one another. We apply oxidation using sodium periodate. Okay, we'll cleave this bond, oxidative cleavage. Okay, and we get the desired target molecule. Suggest a synthesis of 6-bromo-6-deoxy alpha D-galactopyranose from D-galactose. Well, this is the structure of target molecule. Starting from D-galactose, we draw it here in the chair form, but if I transfer it to the line and wedge structure, will be OH in the back, OH down in the back, OH up, so up, CH2 up, so it will be up. Well, so these two H's are close to each other. These two H's are close to each other. Reacting that with acetone acid as a catalyst, we get the diacetonide on carbon OH's carbon 1 and 2 and 3 and 4, leaving the primary hydroxyl group free. Now we react that with HBr or Amer reagent, triphenylphosphine and carbon tetrabromide. We will get the carbon bond on carbon 6, replacing the OH by Br. Then we hydrolyze this compound, hydrolyze the cyclic acetals with dilute acid. We get the OH free back and the target molecule, 6-bromo 6-deoxy alpha digalactopyranose structure. The mechanism here for Amer reaction: triphenylphosphine react with the carbon tetrabromide attacking the Br. The Br, 2 electrons here, carbon will go to the carbon, forming the anion and the cation on the phosphorus. This anion will react with the H deprotonate alcohol, forming the alkoxide. The alkoxide oxygen will attack on phosphorus, forming this species, making this as electrophile, stronger electrophile. So Br minus will attack on the center here and forming triphenylphosphine oxide and alkyl halide. See you next lecture.